Hey everyone, welcome back to another lesson. Today we're going to talk about complex numbers. Okay, an, it's numbers that you don't see. That's weird for me to say that, isn't it? But I'm excited to teach you this. This is actually a really cool concept. Before we jump into what a complex number is, let's talk about numbers in general. We haven't talked about those in a long time. So let's make a quick diagram. Here are all my real numbers. Visually pretend that there's some numbers in here. Okay? And we have, I have another box over there. We have all these little subsets that are within the realm of real numbers. I think this is good enough boxes. So, when you were, barely walking and you're trying to learn what a number is, you started with 1. You went to 2, 3, 4, and so forth. Those were counting numbers. And we call that group of counting numbers natural numbers. Okay, so it's this really pronounced N. It has like a little double bar here in the middle. Okay, so we call those the naturals. Now, you went a little further and you learned about 0. Okay, what is 0 and how does it relate to our number system? So all the natural numbers with 0, we call those whole numbers. Have a little W there, okay? Then, progressing a little bit forward, we learned about negative numbers. Okay, that's 1, 2, 3, 4, etc. And their negative counterparts and what their relevance is to the number system. Okay, we called those integers. And integers, the symbol was a Z. I'm going to run out of space. I got to draw it outside here. A Z, but that Z had like a double bar here in the middle. It was a little bit more pronounced. If you remember, which you better remember, what do you mean you don't remember this? We talked about this months ago. You don't remember from months ago? Sorry, I don't mean to rag on you like that. I'm trying to be amusing. I think I'm failing at it. The capital Z comes from the German word Zahl. I'm probably saying that incorrectly, to be honest, but it's just referencing to German mathematicians, their contributions to number theory. And Zahl, I think, translates to numbers in some way in German. Okay, I don't know the direct translation, so I do apologize for that. So we give them some credit. Now, after integers, we have the next group, which we do as a Q, which has some bars here if you want to be a little bit more pronounced. Okay, it looks a little weird. Q represents the rational numbers, and Q represents quotient, right? Quotient, rational, fractions. See how it all kind of connects, hopefully. Okay, and then we have the real numbers. Now, over here, this separate group, if you remember, is irrational numbers. We could give this guy a symbol. Sometimes we can say it's the opposite of rational, right? So you could see like a nice little Q prime mark, okay, to indicate that. Or sometimes you might see like this little like tilde thing to say it's the opposite of rational numbers. Okay, so your irrationals like square root of 2, pi, e, number e, and so forth. Okay, go into that group. Technically, pi and e goes into their own different group, transcendental numbers. And we're not going to get into that right now. Okay, we're going to stick with just this. Now, what I want to bring up is, are there other numbers besides these guys? Is there something else involved? Well, let's go back to quadratics. We've been talking about quadratics for quite some time. Look at this equation right here. And this is what it looks like graphically. Okay? If I was to solve this guy, you would probably say, well, Mr. McCullough, I don't think there's solutions because whatever number I plug into here is bigger than 1, or bigger than 0 at least. And when I'm adding it to 1, it's never going to give me 0. And I would say you're right. And also, look at the graph. The graph is telling me there's no solutions because technically they have to be crossing the x-axis for there to be solutions. What if I told you there is one? Have your minds been intrigued? Hopefully. There's solutions up here, but you just can't see them. They're just not visible. Okay, what do I mean by that? Well, let's solve this guy. Subtract 1 to both sides. I get x squared equals negative 1. And then I take the square root to both sides. X equals positive, negative, the square root of -1. Now, typically, you would say, nah, that's no solution. You can't have a negative under the square root. But what if we did? What if we actually, looked at this and say, hey, we could do something with this. Maybe there is some other solution to it, okay? So X will equal plus or minus. I'm going to introduce a new concept, a new symbol here. We're going to represent it by an I. Okay, I is imaginary. Okay, that's what we're going to represent that symbol. So I will represent the square root of -1. Now, why still go with this? What's the point behind it? Well, let me tell you this. The square root of -1, if I were to plug it back into the original equation, I would get the solution to work, which someone knocked at my door, so give me 2 seconds. Go ahead and solve that. Plug -1 in and see if you get the right answer. All right. Hey, how's that for a pause? This is how you know it's live. All right, if I plug this back in, which hopefully you did, okay, and I was to solve this, the square root of -1 squared is just -1. Don't they undo each other? And then +1 does indeed give me 0. This has some reference to it. There's something about it that actually makes this work, okay? So we're going to introduce, like I said, it's going to be called an imaginary number. You really don't see it. And we're going to work with this just a little bit. Now, let's talk about the next part of it, and that's going to be the powers, okay? The powers of I. So if I just had I to the first power, we know that's represented by the square root of -1. Let's continue. I squared. What would that equal to? Well, let's expand it. That's what? That's I times I, right? Each I is represented by the square root of -1. And if I multiply these two together, I get -1, right? Just recall, quick recap. If I took the square root of 3 times the square root of 3, okay, I get the square root of 9, which gives me 3. In other words, I'm getting what's underneath the radical when I'm finished with it. Does that make sense? Okay, same principle as it is up here. All right, next, I cubed. Okay, what would that value be? Well, we can break this down by its powers. That would be what? I squared times I would give me I to the third power. All right, so I squared I know is -1, right? We talked about that in the previous. And then times I, which would just give me -I. Okay? And the final one, which, why am I saying the final one? Why do I want to go past I to the fourth? Interesting, isn't it? Maybe there's something to it. I to the fourth we could break up as what? I squared times I squared. Now each individual I squared is a -1. Okay? And then -1 times -1 gives me a +1. Okay? Now, once again, I'm trying to intrigue you a little bit. Why did I stop to I to the fourth? Why don't I continue to see what the other I powers are? Well, there's a reason for that, and I have an exit slip that I want you to try out after watching this video. I want you to figure that out for yourself, okay? And we'll talk about it a little bit later, all right? Questions, concerns, dilemmas? You're always quiet. I wish you would speak up so I know what you're saying. We have a quick history of numbers, right? Where we started from, where we're finishing, and then we came up with an equation that didn't have a real solution, but we could treat it as an imaginary solution. All right, which is pretty darn cool. Okay. Let's go ahead. We're going to try a couple examples, and then that'll be it for part 1 of this video. Part 2 will cover what a complex number is, because I didn't get to that, right? I talked about imaginary, but I didn't talk about what complex means yet. That's coming. All right? It's like a cliffhanger. Stay tuned. Episode 2. All right. So knowing this fact about imaginaries, and I'm going to leave this off to the side so we can reference it. Let's go ahead and simplify a square root that has a negative. Okay. First one, square root of negative 28. Typically, when you got to that answer, you're like, oh, can't do it. It's not going to work because square roots, remember, that pretty much goes with distance. We're talking about distance a lot of times with that. But in this case, we can. Remember, when you try to break this down a little bit, it's a factor of just like products. Okay, we could break a square root up by products. And I'm going to factor out a negative 1. And what I have left is the square root of 28. Now, the square root of negative 1 becomes an I. We know what that is. We just discussed that that's what we're representing it. This one's done. Now look at the square root of 28. We could actually break that down a little bit further, right? And if you recall from previous lessons in your previous math classes, if I want to break down the square root of 28, it has to be 2 numbers that multiplied to that. One of them has to be a perfect square, and you want it to be the largest perfect square possible to eliminate other steps, more work, I should say. And the 2 that come to my mind that would work for this would be 4 and 7. Okay? Now, square root of 4 gives me 2. That's done. It's finished. Can't be simplified further. Square root of 7 doesn't really break down any further than what it needs to be. We could call that prime if it doesn't break down a little bit further. Now, what I have here circled is this guy broken. It's done. It's factored out fully. I put this all together. It would be 2i times the square root of 7. Okay, that's what this simplifies down to. That's pretty cool. Before, you couldn't do that. A couple things about notation, and tomorrow we'll kind of review that again. One, the I, okay? Typically, it's always out in the front of the radical. You don't want to put the I over here because it looks like it's underneath the square root, and that's not good, okay? I is getting rid of that square root, right? We're saying that square root of negative 1 is I, so you don't want to put that back underneath. So keep it here. If you want to put it on the outside even further, like put I first, that's fine. You can do that. I've seen people do that before in the past, and technically that's not really destroying the integrity of the number itself. It's still the same number, but certainly you can put that in the front. Okay? All right, so that's one use of an imaginary number. It allows us to break down a number that can't be broken down originally because it wasn't a real number. All right? Okay, let's try another problem out. Let's do some multiplication here. Okay, another example. Negative 3i times 2i. I want to simplify this guy. I want to be very clear. I'm trying to make these videos shorter. All my examples, I have a lot more of these in my notes, and they're uploaded for you, so please look at those other ones and try them out, okay? Now, for this guy, what I would do first, multiply the real components together, then the imaginaries, okay? And then see if there's anything left to simplify. So for the first one, negative 3 times 2 is negative 6. I times I becomes I squared. I is like another variable to you. I want you to treat it as such, okay? X times x is x squared. I times I is I squared. You're not done yet. You always want to see if you could simplify a little bit further, and I can. I know what I squared is, right? We said that I squared is negative 1. I'm going to go ahead and substitute that into here. Okay, so negative 6 times negative 1 gives me a positive 6. All right? So we started out with multiplying 2 imaginary numbers, and we got a real number. That's pretty darn incredible, isn't it? I think we did that at the beginning of the lesson, right? Square root of negative 1 squared. When I multiplied an imaginary by itself, I got a real number. I'm getting the same result here. I'm getting a real number. it's showing you there's some connectedness to this. Now, even though visually with a quadratic, we didn't see that solution, but it did exist. And we're kind of seeing algebraically how this is all working out, which is really cool. Okay, so 2 good examples here. One of breaking down a square root, just take the I out, and one where you're multiplying 2 imaginaries together and simplifying the result. Okay. All right, let's continue. And I would like for us, I'm going to erase this. Well, no, I take that back. I'm going to erase this one. I want to keep this one up just for right now. We'll make this example 3. Okay, let's do square root of negative 12 times the square root of negative 2. All right. What do I do? Well, I'll show you. My first step, I know each one of them has an I. Now, I'm not going to break this part out first. I'm going to go right to the I part, and hopefully you're okay with me doing that. So I'm going to factor an I out of the first term and an I out of the second term. Okay, just like that. Next, I'm going to multiply these guys together. So the imaginary parts I'll multiply, and then the radicals I'll multiply together. I times I gives me an I squared. Square root of 12 times square root of 2 gives me square root of 24 for that guy. Now, simplify. I squared is just a negative 1. Okay, so I'll just circle it so that way I know it's completely finished. Now, square root of 24, I'm going to break it down to 2 factors, one of them being a perfect square, and I believe that's going to be what? 4 and 6 for those guys. Okay, square root of 4 times square root of 6. Now, some of you might argue, can I do square root of 2 and square root of 12? Yeah, I mean, they're not perfect squares, and when you break it down, it gets a little messy. There's a lot more work involved. That's why a lot of math teachers prefer that you factor with a perfect square. All right, you're making your life a whole lot easier. Square root of 4 is a 2, and square root of 6 does not break down any nicer. If you think about it, 2 and 3, square root of 2 and square root of 3 isn't helping us. Now looking at what I have here, I'm going to multiply everything together. Negative 1 times 2 is negative 2, and then square root of 6 comes after that. Okay, so there it is, fully broken down. When you're approaching these problems, try to keep that distinction in your mind, that look at the imaginary part, simplify it, and then look at the real part and simplify it, and then just kind of combine those guys together. I think that's a great approach to simplifying and just working with these values. Okay. All right, we're coming up on 18 minutes. Wow, man, time is flying, isn't it? Let's see. Do I have one more problem? I do. And then that'll be it for part 1. Okay. I just have to find it. I got papers everywhere. You can't see my mess. But I have a mess here. I have quite the mess. Here it is. Okay. Last example. And we'll erase this guy. And what I'm going to do, notice, I'm not breaking down anything i's as of yet. This looks like a normal, ordinary equation that says, hey, just solve this guy. Okay, I could do that. First step, isolate the variable. I'll subtract 20 in order to do that. I have 5y squared equals a negative 20. Next up, I'll divide both sides by 5. Y squared equals negative 4. This is where your math mind's telling you, ooh, something's not right, because no matter what number I square, it's never going to be a negative. But now we're kind of accepting that notion that that's okay. All right, it's in that imaginary number world. Square root both sides, we get y to be equal positive negative the square root of negative 4. Now, what should I do after this? Well, we know what to do. We could simplify it based on what we did previously. So y is going to equal plus or minus. I'm going to factor an I out. I'm sorry, positive, negative. I'll factor an I out. I'm left with square root of 4 And then I know what the square root of 4 is, right? Isn't that just 2? So it could be 2i together. Now, if you want to put I first, that's fine. That's no big deal. So there's 2 answers to this. It's positive, negative 2i. Would make this guy work. In other words, if I were to graph this, it's never hitting the x-axis. Okay? I know it says y squared, but it could be a squared or whatever. It's whenever you graph that function, it's not crossing an axis. Okay, so therefore, no solutions. But we know there's no real solutions. Doesn't mean there isn't imaginary ones like it is here. Okay? All right. 4 examples and a brief history on just some numbers. Hopefully some of it you remember from the beginning of the year. If not, that's okay. But just kind of showing you where does this negative 1 come from and its importance. Okay? As you can see, it kind of intertwines all of our number systems here, little number subsets. I'll talk about all the rest of this in part 2 of the video. Other than that, have a good day, guys. Hope you have a good one. See you in the next lesson.